Okay, let's talk about free fall. So we've experienced and then we understand an equation that would look like this in the horizontal direction. And the only difference really for free fall, and then really we can look at all of these, right? The big three, right? Our position equation, our velocity equation, and even the v squared equation. All of these still work in the vertical direction. And so when we start talking about an object in free fall, what we mean by free fall is an object under the influence of gravity only. And so when we say free fall, really what we mean is no drag. No drag forces. And it turns out that gravity is a little more complicated than what we say right now, but as long as we're not way away from the Earth, like a significant distance compared to the Earth's radius away, then we're going to fall under little g. Okay. The real model for the force of gravity, and again we're going to explore this much later, would look something like this. Gravity is the mutual attraction of two masses, and so the real force of gravity is capital G, which is the universal gravitational constant, which is 6.67 times 10 to the negative 11th. The product of the two masses, usually it's like the mass of the Earth and the mass of the person, and then divided by r squared, where r is the distance between the two masses, and they call this like an inverse square law. We currently don't have to worry about this, right? What we know is that if we're talking about being on Earth at the radius of the Earth, meaning the surface of the Earth, then these guys right here is what little g is. So if you take those numbers, you end up with little g being 9.8 meters per second squared, meaning something in free fall will accelerate at 9.8 meters per second every second it's in free fall. So if you drop something after 1 second, if you drop something, it's going to be then going down, of course, 9.8 meters per second after the first second. After second 2, it's going to go be 19.6 meters per second, because it's going to, in this case, speed up 9.8 meters per second for every second. That's what little g is, and it doesn't matter what it is. And so we can start talking about all sorts of things. All of these turn into a little g, and we know the direction is down. Okay, so let's say we take something and we drop it from a building. So instead of this, we're like, okay, instead of the position equation that would look like this, what happens if we drop something? Well, usually we're going to start talking about y. The building height might be y naught, and maybe we actually just use h for that. If we drop it, then v naught is equal to 0, and instead of some random acceleration like in a car, we know that the acceleration is going to be down, so we're going to use a negative, and the value of the acceleration is going to be 9.8. And so then we know what this is. And again, whether this is h, whether this is h naught, is really kind of up to you. A lot of people are just going to leave it as y naught. And so if you told me the building height, and you want to hit the ground, you could use this equation to figure out how long it will take to hit the ground. Right? So let's say we're at a building height of 40. We would say something like this. And if we solve that equation, we would get the answer, right? This is really close to 5. We move that over, it's like the square root of 8. So I'm just doing this in my head because I don't have my calculator on me. The square root of 8 is probably something like, I don't know, 2.7-ish seconds. So this would predict that an object, and again, it doesn't matter what object, and you've probably already watched the ball versus feather video, which shows you that in a vacuum, a bowling ball and a feather are going to both fall at the same rate. They both are going to accelerate towards the Earth. They're mutually attracted at 9.8 meters per second squared. Again, obviously in the real world, when we drop things, they all don't fall at the same rate because there's drag. But in physics right now, all our things are in free fall, which means that there are no drag forces. Okay? Okay, let's say I throw something up. Throw. So we've thrown up. Something is thrown up. So we take a ball, we chuck it up at some, I don't know, let's say just 10 meters per second. And let's say we want to know how long it takes to get up. Okay? What if I just want to know how long it takes to get to the top? Well, at the very top, won't the velocity be 0? Don't I throw it at 10? And don't I know the acceleration rate is down at negative at 9.8? And then I solve for t, and you're like, wait a second, that's really easy. T is going to be really, really then close. Oops, to 1 second. Of course it is, right? If you throw something at 10 meters per second, and we know that gravity pulls down at 9.8 meters per second squared, meaning it, in this case, is going to decrease your velocity by 9.8 meters per second every second, then it's going to take 1 second. What if you were interested in how high this thing went? Well, maybe you want to use the v squared equation then. If you're interested in a distance and you know an acceleration rate, and you don't really even care about time, then if you just want to know how high something goes, maybe you want to use the v squared equation. We know that if we want to know how high it is at max, the velocity, the vertical velocity is 0. The original velocity was 10. This is going to be a minus because in this case, the acceleration rate is opposite the initial velocity, and the velocity is up and the acceleration is down, so it's going to be a minus 2g, which is 9.8, and then let's say h, because we know this is a vertical distance rather than this. Again, this is going to be 100. This is really close to like a 20. And so then the height is going to be then really close to 5. And again, I know I'm rounding in this video, but it just saves me the time to typing in the calculator. So this object is going to go up around 5 meters. So I can find max height. I can find the time it would take to go up and down. I can drop things. Any of these old things I can do, I can just do now in free fall. And the only thing we're saying in free fall is that these horizontal equations become vertical equations, so we usually replace them with y's or h's, and that the acceleration rate isn't some random car acceleration. Right? We did problems where we were pushing the gas on a car and the acceleration rate was 3, or we were braking and the acceleration rate was -3. Well, now when we start talking about free fall, it's just a known acceleration rate. It's always going to be down, so this is always going to be a minus 1/2 gt squared. Now the question is this always a minus? Well, it's going to depend. It's going to depend on whether the initial velocity is up or down. Again, this sign in the v squared equation is always going to be negative if the velocity and the acceleration are in opposite directions. In this case, velocity was up and acceleration, of course, is down, so that's going to be a minus sign, right? The acceleration rate is slowing us down. Here, velocity was up, acceleration was down, and so there was a minus sign. If they were going together, so if I did something weird, like let's say I was on top of a building and I threw something down. Let's say I threw it down at 20 meters per second and I was at a building height of, let's say, 40 meters. Now I can say, well, okay, this standard equation, my height at any moment in time, is going to be some initial height plus vt minus 1/2 gt squared. So then the height of my ball is going to be some 40, but since I threw it down, I got to use a negative 20t minus 1/2 gt squared. And so if I wanted to know where I was at any moment in time, I could just plug in the t value and find this. If I wanted to know when it hit the ground, well, then I'd have to solve this quadratic equation. Solving this equation, I could use the quadratic formula. I could graph it, and if it factored easy, I could factor it, but that's the equation. If I wanted to know the velocity at any moment, well, I'm using the velocity equation. The velocity equation says that this is going to be a negative 20 minus gt. That tells me how fast I'm moving down, and of course it's going to be negative the whole time. And you see how these two are the same sign? Because this was down and of course this is down. Again, if I want to know how fast I was moving after 1 second, it's going to be really close to 30. I started at 20, and I know what gravity does. Gravity speeds me up at 9.8 meters per second every second. So if I plugged in 1 here, of course I'm going to get something like negative 30 meters per second down. if I use the v squared equation. Okay, that's the standard v squared equation. It looks like that. And let's say I want to know how fast am I moving after I've gone 20 meters. Okay, so let's find VF. So I started at 20, but in this case, am I going to use a positive or a negative? Well, I have to use a positive. The velocity is down and the acceleration is down, so the acceleration is speeding me up. So I need to do 20 squared plus 2g. And what did I say? How fast am I moving after going 10 meters? I forgot what the story was. Let's say 10. Okay? If I solved for VF here, this would be figuring out how fast I'm moving down. If I started at 20 meters per second down, I accelerated at g for 10 meters. If I wasn't interested in time, then I'd use the v squared equation. If I was interested in how fast I was moving after a certain number of seconds, well then of course I'd just use the velocity equation. But I'm arguing that the big three equations, the position equation, the velocity equation, and the v squared equation, are of course still true in free fall. Free fall is simply replacing the acceleration and making it always negative in the position equation and making the value of the acceleration 9.8. The reason it's 9.8 is really just based on the fact that the radius of the Earth is a certain value. This is a universal gravitational constant, true everywhere in the universe, and then the mass of the Earth. So if you went to the moon's mass would be different, the moon's radius would be different, meaning you'd be further away from the center, or you'd be actually closer to the center mass of the moon, and then g would change. G on the moon is something really close to our g over 6th, all right? So it's really close to 9.8 dividing by 6 is the acceleration on the moon, because the moon's mass and the moon's radius is different. But these equations are still the same. Okay, let's look at one more thing. Do you see this equation right here? This comes up enough that we just shorten it. It's not a new equation. This is our standard equation. If I drop something and all I want to know is the time, right? Let's find the time it takes to drop something from a certain height. Then don't I want it to hit the ground? Aren't I dropping it from an initial height of h? And if I'm dropping it, isn't that 0? And don't I know that it's under the influence of free fall? Do you see how the standard position equation becomes 0 equals h minus 1/2 gt squared? But if I rearrange that, don't I really get this? And so this is an equation we use a lot. It's kind of like just the drop equation. If you want to know how long it's going to take to drop something from a certain height, this equation is just the shorter version of that big long one, but it's not any different. This does not tell you the height of the object. This tells you how long it takes to fall a certain distance h. That's not the same thing. If I'm here and I drop something and I want to know how long it takes to, let's say, drop 30 meters, I can just plug in 30 for here. Again, that's the same thing as figuring out when I'm at, if the whole thing is 10, I'm at 10. I could put a 40 here and a 10 here, and that difference is the height fallen. That's the same thing as just putting a 30 in here. You have to think about when this is useful. Certainly, if you want to know where you're located, this is not a good idea. That's just going to tell you how long it takes to fall a certain distance. But we do end up knowing the full distance, and we end up dropping it a lot, so that is a fairly useful quantity. Okay, hopefully this video did an okay job of showing you that the big three standard equations can now all work in vertical situations, and all we have to do is replace the acceleration by g. We have to be careful of whether it's a positive or a negative. G itself is 9.8, and we always put the negative sign there. Most of the time we're going to put a negative. Every now and then, if we're throwing something down, then it is going to be speeding up, and then we do need a positive there. Okay?